electron configurations. Now that we have the basic structure of a hydrogen atom, it's time to expand this into multi-electron systems. We've talked about energy level of a particle in a box in hydrogen, and now we're going to see how this varies for multi-electron systems. We're no longer able to solve the Schrödinger equation exactly, and we have to use approximations. This is far, far beyond the scope of the class, and so we won't be doing that here. Instead, I'm going to be showing you the results and showing you some tricks using the periodic table so that you're able to use these results quickly and efficiently. In this video, we'll use the periodic table to learn the order of the energy levels of the orbitals. These are actually given by the wave function, however, the periodic table just lends itself to being a quick trick for helping us do this. We'll write the electron configurations for atoms and ions, and I've given a third objective as a little bit separate because it is a bit more difficult. We'll write the electron configurations for atoms and ions that are in the D block that have exceptions to the filling rules. Now let's draw out the orbitals in the correct order of energy. I've drawn out two diagrams. The first is for hydrogen and hydrogen-like ions. The second is for everything else. I'll talk about an easier way to remember this ordering in a minute. First, let's look at the main difference between the two. So look at the two and see if you can figure out what doesn't match. In the first one, all of the subshells in an energy level are degenerate. So by subshell, I mean that when we look at the 3s, 3p, and 3d, they're all the same level. So every subshell within that energy level are degenerate. When we come over here, we can see that only within a subshell are they degenerate. The 3s is different from the 3p, which is different from the 3d. In multi-electron systems, the subshells are going to be different in energy. Let's think about why this would be different. Well, in multi-electron systems, there's going to be electrons in these lower energy levels that shield the higher energy levels. So in a one-electron system like we have over here, if the one electron is in the 4p orbital, there is nothing down here. These are just empty orbitals, which means that no shielding takes place. Meanwhile, over here, if we are all filled up and we're in the 4p, these all have electron density in them, and that's shielding the electrons in these energy levels, and that causes a difference in energy. Now, I have a couple of other questions down here. Here I have drawn hydrogen with atomic orbitals higher than 1. Now, is that correct? Why or why not? This often comes up on exams. If I ask you to draw a hydrogen or a hydrogen-like ions electron orbitals up to a certain level, many people will stop at 1. Well, of course it's possible, and we've already done a ton of problems where we've used that. Think about all of our spectroscopy problems when we were promoting electrons from the n equals 1 to the n equals 4 level. There was an n equals 4 level. It typically is empty if something is at the ground state, but that doesn't mean that it doesn't exist. And so yes, you can draw a hydrogen or a hydrogen-like ion with a higher energy levels, even if they're going to be empty most of the time. You can always promote the electron up by giving it a laser pulse. Now let's look at how we can tell the ordering of these energies, because you don't want to have to memorize the chart that I had on the last page. There are some memory tricks for doing this, but most of them cause you to do a lot of work and aren't efficient and don't actually teach you that much about chemistry, and so I'm not going to teach them. Instead, I'm going to teach you how to do it using the periodic table. So here's an expanded version of the periodic table. This version doesn't fit well into textbook covers, and so therefore publishers don't use it. However, it is the most useful for filling in of energy levels and making electron configurations. If you then want to use a normal periodic table, just keep in mind that that bottom block, that F block, fits in to the table like it's shown here. So think of this whenever you look at your periodic table in the book. This way you can make electron configurations without having to memorize the order. So we'll do a few examples filling into the chart on the previous page, and then start using this to fill in. You'll also hear me constantly refer to blocks on the periodic table. We can see here why. This we'll call our S block. because whenever we're talking about any of these orbitals, the last filled electrons are the s orbitals. We'll call this the p block, because whenever we're talking about something here, the last filled electrons will be in the p orbitals. We call these metals here and here the d block, because the last filled orbitals are the d electrons. And this area, the f block, because the last filled orbitals are the f orbitals. We'll come back to this later and walk through these very quickly, but let's first talk about how to do it using the chart on the previous page and then move on to this. Here we'll do an atomic energy level diagram and then do the electron configuration using that for carbon as our first example. Let's start with the diagrams that I drew out for multi-electron atoms. Because I want to show you what not to do, I've started with 2 of these. There are rules for how to fill the electrons into the orbitals. First, we'll count how many electrons we have, which for carbon is 6 total, and then we'll start at the lowest energy and fill up. Each orbital can hold 2 electrons. If there is only one orbital of a particular energy, simply fill it till it's full. When we get to the p orbitals, though, we're going to have a choice. Do we fill one orbital or do we go across the row? Hund's rule states that it is better to go across the row first. So you'll fill across degenerate energy levels before filling each individual orbital. So if we start here and we start filling up, what does that Hund's rule really mean? For the first 4, we just fill into the orbitals. There isn't any degenerate orbitals to worry about. But when we get to this p, we have this problem. Where do I put that second electron? So this would not be correct according to Hund's rule. Instead, we need to fill it like I have down here across the row first. If we had a 3rd electron, like in nitrogen, we'd fill into this box. And then when we go to the 4th electron, if we had something of oxygen, we would double it up at that point because this row is already filled. Now let's talk about how we write this without drawing out the whole diagram. These diagrams are really nice when we're first learning how to do this, but it would get a little bit annoying to have to write this whole diagram out every time. So the shorthand notation is to write exactly what we have for electrons. So here we have 1s with 2 electrons in it, 2s with 2 electrons in it, and 2p with 2 electrons in it. Or in other words, 1s2, 2s2, 2p2. Now let's write the electron configuration for cobalt. Because we're still learning, we're going to fill into the electron energy level diagram first and then write out the electron configuration. First, we're going to count up how many electrons are needed by looking at the periodic table. This gives us 27 that we need to do. We'll fill according to the rules 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, as we get to the last ones, we'll want to be careful to fill across first and only then go back and double up the electrons. Now we need to write this out in a form like we did in the last slide rather than having to draw the whole picture. So we can do this in 2 ways. We can first write out 1s2, 2s2, 2p6, 3s2, and so on. Now you can see that this is a little long-winded as well. So a shorthand notation is by going back to the last noble gas, which in this case is argon, and only adding in the additional electrons past the noble gas configuration. Now, pretty much always, I would prefer that you use this. It's much shorter, you're much less likely to make a mistake, and it's much simpler to read, and everybody still knows what you're talking about. Now that we've had some practice with electron configurations, let's do some without using the diagram, since that isn't something that you're going to want to memorize. Let's use just the periodic table. We'll do nitrogen first. Here we have our 1s orbitals. I want you to pretend whenever we're doing these that helium is over here. We put helium over here because it's a noble gas, and so therefore it has similar properties to the rest of the noble gases. But for electron configurations, you want to think of it as being here. So we need to count our way over to nitrogen. We'll start with the 1s. We're not to nitrogen yet, so it's 1s1, 1s2. So 1s2 is filled. We come down here. 2s1, 2, so 2s2 is filled. Now we come all the way over here to p. And we have 2p, 1, 2, 3. So let's write this out, and then we'll do it again. So here I have it written out, and we have 1s, 1, 2, because we're imagining helium here. 2s, 1, 2. And over here, 2p, 1, 2, 3. So here I have this written in both the normal format and the noble gas configuration. Of course, here the noble gas configuration doesn't actually save you much writing, so either way is fine, but that will be very handy later on. Let's do another one. We'll do magnesium. Here, we'll start from the beginning again. 1s, 1, 2, because that's filled. We're imagining helium here. 2s, 1, 2. Coming over here, 2p, 1, 2, 3, 4, 5, 6. Now we come down here, and we're at 3s, 1, 2. So we'll write this out. And I went straight to the noble gas configuration here to save us some time. So I said, well, here we're at magnesium. I know that neon is the last noble gas, so I'm going to save some time by just writing out neon here. And then add in whatever else is there. So 3s, 1, 2. Let's do another example. We'll do one that's a bit more complicated. Here we're in the D block, and so we have to be a little bit careful because the very first time that you see a d orbital is in the n equals 3 level. And if you're saying, well, why is that? Well, that has to do with the rules for our quantum numbers. Remember, the first time we're allowed to have an L equals 2 is when n equals 3. And so this very first one here is actually 3D. Other than that, it's the same. We could start from the very beginning if we wanted and go 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, 4p6, or we can save ourselves some time and just start straight with argon. So if we start with argon, we'll start here and only work our way from there. We have 4s1, 2. Now we get to the D's, which starts with a 3. So it's 3D, 1, 2. So again, we start with the last noble gas, which is argon, and we fill in 4s1, 2, 3D, 1, 2. Now let's do arsenic. Let's start with the last noble gas, which is argon. We come over here, we have 4s1, 2, 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we're back to the P's. So the P's and the S's are that same n equals 4. And so this is still 4p, 1, 2, 3. So again, we start with argon. We do 4s1, 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we're back to the 4p3. So all you really have to remember using the periodic table is that your D block starts with 3, your n equals 3 level, and that your F block starts with starts with n equals 4. If you can't remember that, you can use your rules for quantum numbers to remember it, but because we do these a lot, it's a good thing to also just have in your automatic memory. We can do electron configurations for ions as well. To do this, we're either going to add or subtract the appropriate number of electrons. Let's do an example of a calcium cation. We'll start by writing out the electron configuration for calcium. I've filled in the electrons already. This gives us an electron configuration as follows. If we want to make the +2 cation, you just remove 2 of the electrons. And for the most part, you'll remove the ones in the highest energy level. There is exceptions to this that we'll talk about. So we remove those 2 electrons to give us calcium 2+, and we'll write our electron configuration. You can see for the noble gas configuration, this actually, just because we removed these 2 electrons, these 4s2 electrons, just gives us argon. Some professors require you to write out from the last noble gas. I, however, don't care. If you want to just write it as argon, that's all right. You could also, and you'll see this sometimes, leave that 4s there and write a little 0, just to say, this is where I took them from. You'll see that especially in books when they're trying to show you things, but you're not required to write it. It is fine if you do. Now let's do an example where we make a negative ion, or an anion. We'll start with chlorine and make chlorine minus. Here I've already drawn out the atomic energy level diagram of chlorine. If we want to give it a minus charge, that means that we're going to have to add one more electron. Here I have the electron configuration. So we have neon, 3s2, 3p5. To make it a negative, we'll add 1 electron to this empty orbital. And you can see why it would want to add an electron here, since that makes it into a noble gas configuration. So we add in this electron, which gives us 3s2, 3p6. There are some situations that arise that don't follow this typical pattern of filling low to high and removing from the highest level. Here I've listed them out, and we'll go into each in more detail in the following slides. First, we'll talk about positive ion exceptions. When you're in the D block, so you have something that's 3d4, 5d3, etc., you're always going to remove from the s orbitals first. Even though that these aren't the highest energies, actually the d ones are, you're still going to remove from the s orbitals first. Due to the fact that half-filled and fully filled shells are more stable, if 1 electron can be moved up from the s orbital to the d orbital to make a half or fully filled d block, then it will be promoted. 1 and only 1. You are not allowed to move 2 up. The f block also has a lot of exceptions, but these aren't quite as systematic. There's definitely reasons for them, but the reasons go beyond the scope of the class, and so we're not going to worry about them. If I ask you for something in the F block, I will pick one that has a normal filling pattern, or it follows all the rules. If you're interested in some of these, you can see the book or the internet to see where these are, or of course come to office hours whenever and we can talk about them. Now let's think about why we're able to be so fluid with these electrons, especially between the s and the d orbitals. You'll notice in the energy level diagrams that I drew that I tried to keep the s and d orbitals, for instance the 4s and the 3d orbital, very close to each other. And that was done on purpose because they do have very similar energy levels. The d is technically a bit higher, so for instance a 3d is a little bit higher than a 4s, or a 4d is a little bit higher than a 5s. But not by very much. Because of this very slight difference in energy levels, you can get added stability from a half or fully filled energy shell. So that added stability makes up for the fact that you're in a higher energy level. This is why you only get to move 1, because by moving the electron up, you are putting it into a higher energy orbital, and that's less favorable. However, if it's half or fully filled, it's enough to make up for it. It's not enough to make up for moving 2 electrons though, so you're only ever able to move 1. Let's do a few examples of these. Here I have cobalt, which is well into the D block. You can look at this on the periodic table if you'd like to use the periodic table. For the sake of explaining, I've used the atomic energy level diagram. Now, if we want to make a cation out of cobalt, we're going to remove from the S block as opposed to the D block. So this is a sort of exception that also is a rule whenever you're in the D block, and only the D block. So when we remove our electrons, we'll remove these 2 electrons to give us this electron configuration, which down here you'll see now the 4s electrons are gone. This is, again, where you'll often see a 4s0 written, and that's okay. You can do it if you want. You don't have to if you don't want. Now let's look at a few of the species that are exceptions when it comes to the neutral species as well. So this is that second thing that I talked about for exceptions. Half and fully filled d subshells are very stable. If promoting a single electron from the s to the d orbital will make the subshell half or fully filled, it will stabilize the overall atom enough that it is the most favorable electron configuration. For instance, if we were to draw neutral chromium following the normal rules, it would look like this. However, since the promotion of one electron gives us a fully filled or a half-filled d shell, we can promote one electron up. Even though it is a higher energy level, the increased stabilization of the half-filled d subshell lowers the total energy. This is our neutral chromium electron configuration. 4s1, 3d5. Now we'll do an ion of chromium. We start from our neutral chromium. I want you to make a +1 ion, and so we need to remove one electron. Just like before, we remove from the 4s orbital first. So this one will go away, leaving us with argon 3d5 as our electron configuration. Now I want you to try to do one on your own. Doing exactly the same thing that we just did with cobalt, do this for copper and copper 1+. Pause the video, come back when you think you have it figured out. Here we have what neutral copper would look like if we followed the normal way of filling orbitals and just went from low to high. However, as we saw previously, if you get to fill or make a half-filled d subshell, then you should promote an electron up. And so you should have moved this electron up to create a neutral copper configuration with one electron in the 4s, and then the d1 will be filled. So you'll have 3d10. Now, I also asked you to make copper 1+. So if we need to remove an electron, since we're in the d block, we're going to remove from the s orbital first. And so this will go away, leaving us with argon 3d10 for our copper ion. We've done 2 examples of the d-block exceptions now. This same logic can be used to explain why molybdenum, silver, and gold all form +1 ions. In each case, one of the s electrons is promoted to the d subshell, leaving one electron behind. A stable ion is formed by removing this electron. For practice, write out the electron configurations for each of these that I have blocked off. You'll notice I didn't block off tungsten, which is the W. That's because it's an exception to the exception, and so I didn't block that one off. You should now have an idea how to use the periodic table to learn the order of the energy levels of the orbitals. You should be able to write the electron configurations for atoms and ions, or at least will after some more practice, and write electron configurations for atoms and ions in the D block, which are exceptions to the filling rules. We'll of course do a bunch more examples of this in class, as the only way to get good at these and to get fast at these is to do lots and lots of examples.